Imagine thousands of bank transactions happening every second over the internet. How does a bank make sure that transaction data are not tampered with along the way? And how does it make sure it's really you who sent it and not someone else? That is the problem that we are trying to tackle in this paper. We compare two of the most common cryptographic mechanisms used to secure digital banking transactions, HMAC, SHA 256, and also ECDSA. My name is Wijaksara Aptaluhung with name 182230088, and this is a walkthrough of my paper. So there are three questions that we are trying to answer in this paper. The first one is in terms of the performance. Which one is the fastest one? HMAC, SHA 256, or ECDSA? The second thing is about the security. How do they differ when it comes to non-repudiation, replay attack resistance, and also the impact of a key being compromised? And last but not least is the most practical one, is about when should a bank use HMAC and when should it use ECDSA. And to answer this, we built a banking transaction simulation in Python and ran each algorithm 1,000 times so that the result would be statistically meaningful. So before we get into the result, let me explain the concepts about these algorithms so that it makes sense without all of this plethora. So the first one is about HMAC SHA 256. So basically, HMAC SHA 256 works like having one shared keys that is held by both parties, the sender and also the receivers. That key is also used to stamp the transaction data, and if the stamp matches on both sides, then the data is valid and really came from one person or someone who is holding the key. But because both parties hold the same key, neither of them can be used to prove that it was really this person who sent this and not me, since both of the sides could have produced the same stamp, and that is why HMAC has no non-repudiation. On the other hand, ECDSA is fairly different. Here, each party has two keys, a private key that can only one person hold, which is them, and also a public key that can be shared with anyone across the world. And when they send a transaction, they sign it using their private key, and anyone else can verify the signature using the public key that they have, but they cannot forge it without the private key. So that is why ECDSA provides no repudiation. The signer cannot claim that that wasn't me. Think of it like this. HMAC is like a shared password that you and the cashier both know. Meanwhile, ECDSA is more like your actual signature, something that only you know and only you can produce. So for the experiment, let me show you the code real quick. Okay, here we try to simulate a transfer transaction in JSON format. As you can see here on the code, we're using a JSON format containing transaction ID, sender, the receiver, the amount, and also the sequence number to prevent replay attacks. And the data is serialized into a canonical format, and then it is processed in two ways based on the algorithms that we are trying to compare. The first one is the HMAC SHA256 using Python's built-in HMAC and also hashlib libraries to help generate key, compute the MAC, and also to verify the MAC that's been computed and also produced. On the next one is the ECDSA algorithm. We're using the cryptography library with several modules that we're trying to use here. We're using with the P256 curve, the same curve that is used in TLS and also many banking systems, since that is what we are trying to benchmark. And here we can generate the key pair, sign them, and also to verify the sign to make sure that the sign is real and to verify whether the sign is valid and was sent by this specific someone. So everything is ran in the main.py, or we name it as the benchmark.py. Here we're using 1,000 runs, and we run each of the algorithm 1,000 times, and then we print the results that has been done using those functions that has been defined before. And here we already have the results on running this main code. So, and to make it more neat, let me show you the table from the paper that we have built. So let's see one of the most important and also interesting part of this paper, which is the result on the HMAC SHA256 versus the ECDSA. Here, we can definitely see that on key generation time, MAC and or sign time, and also the verified time, HMAC SHA256 is fairly faster if we compare it to the ECDSA. And if you see it right here, the key generation is almost about 900 times faster. The MAC slash sign time is around 280 times faster, but the verification is around 600 times faster. And this basically makes sense. Why? Because HMAC only relies on lightweight hash operations, meanwhile ECDSA requires more computationally expensive elliptic curve point multiplication and also calculation. And if we see it from the size, both of these algorithms um, from the HMAC SHA256, it produces a 256-bit output. Meanwhile, ECDSA signature is around 71 until 72 bytes. It's more than the double of the latter, but it's still relatively small for modern banking methods and also networks. Now let's see it on the second table about the security properties comparison. On the security side, this is where we see that ECDSA actually have a leap of advantages if we compare it to the HMAC SHA256. ECDSA provides non-repudiation, meanwhile HMAC doesn't. And if an HMAC key leaks, both parties sharing that key are affected. If an ECDSA private key leaks, only the owner is affected, and it can easily be revoked independently without disrupting anyone else. And one more important point for the scalability is if n parties need to communicate with each other, if we see it on the HMAC, it requires an n squared keys since every pair needs its own shared secret. Meanwhile, the ECDSA only needs n key pairs. So more institution involved, the more efficient ECDSA becomes for the key management. So let's see it to the outtake for this paper. So when should each one be used? So for HMAC SHA256, this is best to be used on internal communication for example, between microservices within a bank, session validation for internet banking, and also real-time payment systems where latency has to be as low as possible. All parties already trust each other within the same organization, so non-repudiation is not an aspect that needs to be in consideration. Meanwhile, on the ECDSA, it will fit better when external parties are involved. Etc. Let's say it's like open banking APIs, interbank transfers, and also high-value transactions that really need an accountable audit trail that is very, very legal. And as a matter of fact, in Indonesia, we have our own national standard, which is called SNAP. It is initialized by Bank of Indonesia, and in fact, it already requires a symmetrical digital signature for open API payment authentication. So, this paper also proposed that on the real-world applicability, it is better to not only pick one over the other. It is better to do a hybrid approach to breed these two algorithms. In this case, HMAC is used in the internet layer where speed matters and non-repudiation is not something that's critical. Meanwhile, ECDSA, we can use it on the layer that needs legal accountability and also external interoperability. So to wrap up this paper, basically, neither HMAC SHA256 nor ECDSA is universally better. Each of them has its own place, its own pros, and also its own contras. HMAC wins on speed, meanwhile ECDSA wins on accountability and also scalability. Modern banks typically combine both depending on the use case, on how they want it to be used. Okay. Basically, that is the summarization of the paper that we are trying to propose. Thank you so much for the attention and good night.